Voyager to turn its camera back towards Earth, and it was basically amounts to Earth's first ever selfie. And that picture was taken, and there was these pale blue dots sitting.
Get ready for the discovery of a lifetime. Scientists have finally figured out the truth about Oumuamua. In 2017, a mysterious object named Oumuamua flew through our solar system, resulting in a mystery that puzzled astronomers worldwide. Was this fast-moving, cigar-shaped object a simple asteroid, a comet without a tail, or an alien spaceship? As the first confirmed visitor from beyond our solar neighborhood, Oumuamua's origins and nature have finally been solved.
Our own solar system is huge, so even getting a package from the nearest star system, 4.4 light years away, would take over 50,000 years. So this is a really big deal.
Join us as we explore the secrets of Oumuamua and uncover what this object reveals about the universe and our place within it. In 2017, astronomers stumbled upon something truly out of the ordinary. A telescope in Hawaii, known as Pan-STARRS 1, caught a glimpse of a mysterious object hurtling through our solar system at an astonishing pace. They named it Oumuamua, which in Hawaiian means a messenger from afar arriving first. And what a fitting name it was, for this object was unlike anything we'd ever seen before. However, the mystery behind this object has finally been solved by scientists who have revealed shocking news about what it really is. Right off the bat, Oumuamua had scientists scratching their heads. It was moving fast, really fast. It was going through space at a speed that left even the swiftest comets in our solar system behind. But it wasn't just its speed that was turning heads. Oumuamua was also moving in a way that didn't quite add up. It was accelerating, picking up speed as it swung around the sun and then shot back out of the solar system. This kind of non-gravitational acceleration is something you might expect from a comet, but Oumuamua showed none of the usual signs of being a comet. There was no glowing coma, which is the cloud of gas and dust that usually surrounds a comet's core, and no tail streaming out behind it. So what was it? The theories started flying. Some scientists thought it might be a comet, albeit a very odd one, without the usual telltale signs. Others suggested it could be an asteroid thrown into our solar system from somewhere else in the galaxy. And then there were the more controversial ideas. Could Oumuamua be some kind of alien technology? A spacecraft from another civilization, perhaps? But despite all the speculation, one thing was clear. Oumuamua was the first confirmed object from outside our solar system to pay us a visit. That alone made it unique in the world of astronomy. It was our first real glimpse at something from beyond, a tangible piece of the huge, unexplored universe that lies outside our solar neighborhood. And with that realization came a flood of questions. Where did Oumuamua come from? What was it made of? And what could it tell us about the universe beyond our own solar system? When Oumuamua zipped through our solar system, it indeed resulted in a wildfire of speculation and debate. At the heart of this debate was a bold and controversial idea proposed by Avi Loeb, a well-respected astronomer from Harvard University. In his book, Extraterrestrial, Loeb put forth a hypothesis that seemed like something out of a science fiction novel. Could Oumuamua be an alien spacecraft or a probe from a distant civilization? Loeb pointed to several of Oumuamua's peculiar characteristics to support his theory. Unlike any comet or asteroid we've seen before, being more elongated than any known object in our solar system, it also exhibited non-gravitational acceleration, meaning its trajectory couldn't be fully explained by gravity alone, suggesting an extra push that could, hypothetically, be explained by an artificial propulsion system. Furthermore, Oumuamua's surface was shiny, possibly metallic, adding to the mystery of its composition and origin. This hypothesis took the public imagination by storm, leading to widespread media coverage and public interest. However, it also met with skepticism from many in the scientific community who favored natural explanations for Oumuamua's features. Critics of Loeb's hypothesis argued that the acceleration could be explained by natural processes, such as the outgassing of materials when the object was warmed by the sun, even though no such outgassing was directly observed. Despite the controversy, Loeb's hypothesis has played a valuable role in the discussion around Oumuamua. It challenged scientists to look beyond conventional explanations and consider a broader range of possibilities, pushing the boundaries of our understanding of interstellar objects. The debate around Oumuamua and its origins has highlighted the importance of keeping an open mind in scientific inquiry, reminding us that the universe may hold surprises that defy our current understanding and expectations. The debate around Loeb's hypothesis brought to light an important conversation about sensationalism in science. In our quest for answers about the universe, it's easy to get carried away by exciting but unfounded theories. The media, always hungry for a sensational story, can amplify these ideas, spreading them far and wide before the scientific community has had a chance to weigh in. This isn't to say that we should close our minds to the possibility of life beyond Earth. On the contrary, the search for extraterrestrial life is a legitimate and exciting field of scientific inquiry. Projects like the search for extraterrestrial intelligence and the study of exoplanets are dedicated to exploring this very question. But these efforts are grounded in evidence-based science, using the tools and techniques at our disposal to gather data and test hypotheses. The search for extraterrestrial intelligence institute, for example, employs an array of radio telescopes to listen for signals that could indicate intelligent life elsewhere in the cosmos. This meticulous search scans thousands of star systems, looking for patterns or signals that differ from cosmic background noise, which could suggest a technologically advanced civilization. Similarly, the study of exoplanets, or planets orbiting stars outside our solar system, has exploded in recent years thanks to missions like NASA's Kepler and Transiting Exoplanet Survey satellite. These spacecraft identify exoplanets by detecting the tiny dips in a star's brightness as a planet passes in front of it, a method known as the transit method. By analyzing these transits, scientists can infer a planet's size, composition, and even the potential presence of an atmosphere, key factors in assessing its habitability. Moreover, upcoming telescopes, such as the James Webb Space Telescope, are set to peer into the atmospheres of these exoplanets, searching for chemical signatures that could indicate the presence of life, such as oxygen, methane, or water vapor. This approach, combining astronomical observation with spectroscopic analysis, opens new avenues for detecting planets and potentially habitable worlds. These scientific endeavors illustrate a critical point, which is that the search for extraterrestrial life is methodical, rigorous, and based on the gradual accumulation of evidence. Each project builds on the work of its predecessors, refining techniques and expanding our capacity to explore the universe. Through this careful, evidence-based approach, we're expanding our understanding of the universe and our place within it, one discovery at a time. This highlights the need for critical thinking and skepticism, particularly with claims beyond our current knowledge. It urges balancing curiosity with the strict requirements of scientific proof, and the recent discovery that scientists have made about Oumuamua's origin is concrete and based in scientific evidence. So what have they found out that's so shocking? Despite the many assumptions around this mystery being alien technology, scientists got down to the business of finding natural explanations for this interstellar visitor's peculiarities. two compelling theories emerged, shedding light on the mysteries of Oumuamua without needing to venture into the world of science fiction. The first theory is about tidal fragmentation, a concept put forward by researchers Yunjiang and Douglas Lin. They suggested that Oumuamua might not be an entire object, but rather a fragment of something much larger. Imagine a bigger celestial body cruising too close to a star or a planet. The immense gravitational forces at play could literally tear it apart, like pulling a piece of taffy until it snaps. Oumuamua, according to this theory, could be a piece of space debris from such an event, flung out into the void of space to eventually pass through our solar system. This tidal fragmentation scenario isn't just a wild guess. It's backed by computer simulations and mathematical models that Zhang and Lin used to study how objects are affected by close encounters with stars. Their research shows that when a large object, such as a comet or an asteroid, passes too near a star, the differential gravitational forces, stronger on the side closest to the star and weaker on the far side, can stretch and ultimately disrupt the object. This process is known as tidal disruption, and it's a well-understood phenomenon in astrophysics, observed in various contexts, such as the disruption of stars by supermassive black holes. What makes Oumuamua intriguing in this context is its elongated shape, which fit the profile of an object that's being stretched and fragmented by tidal forces. According to Zhang and Lin's simulations, such a close encounter would tear the parent body apart and could also result in fragments with highly elongated shapes, much like Oumuamua's. These fragments, once ejected, would cool down and harden, preserving their unusual shapes as they travel through interstellar space. Furthermore, this theory offers a possible explanation for Oumuamua's lack of a cometary tail. The intense heat experienced during a close flyby of a star could vaporize the more volatile materials, leaving behind a more resilient, possibly rocky or metallic core. As Oumuamua traveled through the cold of space, any remaining volatiles would be buried beneath this hardened exterior, preventing the usual outgassing that gives comets their characteristic tails when they approach the sun. The tidal fragmentation theory also aligns with observations of other space bodies within our solar system and beyond. For instance, comets that pass too close to the sun, or planets often break apart, a phenomenon observed numerous times by astronomers. By applying this understanding to Oumuamua, researchers like Zhang and Lin provide a natural explanation for its properties, one that relies on the known laws of physics. On the other hand, the nitrogen ice hypothesis, championed by Arizona State University astrophysicists Stephen Desch and Alan Jackson, opens up fascinating possibilities about the composition of planets in other solar systems. If Oumuamua is indeed a piece of an exo-Pluto, it hints that the processes that formed our own solar system, with its icy dwarf planets and comets, might be common throughout the galaxy. This could be a crucial piece of the puzzle in understanding how planetary systems form and evolve over billions of years. Desch and Jackson's hypothesis is based on detailed analysis and calculations regarding Oumuamua's observed properties. They suggest that its unusual acceleration, as it moved away from the sun, could be explained by the sublimation of solid nitrogen ice. This process, where solid nitrogen turns directly into gas when heated, would provide a gentle but continuous thrust, pushing Oumuamua along its journey without producing a visible tail or coma typically associated with comets. This theory accounts for Oumuamua's non-gravitational acceleration and also aligns with its observed brightness and shape. The implications of this nitrogen ice hypothesis extend far beyond Oumuamua itself. In our solar system, solid nitrogen ice is found on the surface of Pluto, and its presence on Oumuamua suggests that similar icy bodies exist in other planetary systems. This challenges the notion that our solar system's architecture, with icy bodies in the outer regions and rocky planets closer to the Sun, is unique. Instead, it may be a common outcome of the planetary formation process across the galaxy. Moreover, this hypothesis provides insights into the life cycle of planetary systems. If Oumuamua originated from an exopluto, it likely got ejected from its home system through gravitational interactions, possibly with giant planets or during the chaotic early stages of its star's history. This ejection process mirrored in our own solar system by the Oort cloud and Kuiper belt. Objects suggests a universal mechanism by which planetary systems shed material into interstellar space. Understanding Oumuamua's composition and origin sheds light on the diversity of objects that roam our galaxy and on the dynamic processes that govern the birth and evolution of planetary systems. By studying Oumuamua and future interstellar objects, we gain a unique window into these processes, offering clues about the commonality of the conditions that may lead to the formation of habitable worlds across the cosmos. In the end, while Oumuamua's visit raised more questions than it answered, it also provided a unique opportunity for scientists to test their theories against a real-life interstellar object. Each hypothesis, each piece of data collected, brings us one step closer to understanding the vast, mysterious universe we call home. The arrival of Oumuamua in our solar system was a wake-up call to the scientific community and space enthusiasts alike. It turns out that Oumuamua isn't a lone wanderer in the vast expanse of space, but potentially one of countless interstellar objects that have been ejected from their home systems. This revelation comes from a combination of simulations and calculations, which suggest that the universe is filled with objects like Oumuamua, each with its own story of origins, journey, and eventual ejection into the space between stars. This idea of a vast, interstellar population changes the way we think about our neighborhood. It's more than only stars and planets out there. It's a swirling mix of interstellar travelers, each moving through the galaxy on its own trajectory. These objects could be fragments of planets, remnants of cosmic collisions, or even ancient comets and asteroids kicked out of their home systems by gravitational interactions. But how do we go about discovering more of these interstellar visitors? That's where the next generation of telescopes comes into play. The Vera Rubin Observatory, set to come online in the near future, represents a significant leap forward in our ability to scan the skies. With its wide field of view and powerful imaging capabilities, the Vera Rubin Observatory will be like a supercharged pan-STARRS, capable of capturing vast swaths of the sky in incredible detail. The observatory is equipped with the LSST camera, touted as the world's largest digital camera, boasting a staggering 3.2 gigapixels.
We got the 3.2 gigapixel camera. They have two Guinness records, the biggest one for the biggest camera, and also the one for the biggest lens.
This remarkable tool will enable the Vera Rubin Observatory to take more than 800 panoramic images of the sky every night, covering the entire available sky every few nights. By detecting changes in position and brightness over time, the observatory will identify interstellar objects and calculate their trajectories, offering early warnings of their approach and providing valuable time for in-depth study. The potential for discovery with the Vera Rubin Observatory is immense. By taking regular, almost nightly images of the entire sky, it will be able to spot moving objects like Oumuamua much more efficiently than current telescopes. This means that we're on the verge of uncovering more interstellar objects, each potentially offering new insights into the processes that shape planetary systems and the dynamics of our galaxy. Moreover, these future observations will help us understand the distribution and properties of interstellar objects. Are they mostly icy like comets, rocky like asteroids, or something entirely different? How often do they pass through our solar system, and what are their typical sizes and shapes? Answering these questions will expand our knowledge of the universe and refine our models of how solar systems form and evolve. Oumuamua was just the beginning. With the advent of more powerful telescopes like the Vera Rubin Observatory, we stand on the brink of a new era of discovery. In this era, interstellar objects will be common, each one contributing to our understanding of the universe. Our solar system is not isolated, but part of a vast, dynamic cosmic ecosystem. After much debate and a range of theories, the scientific community is converging on a consensus about Oumuamua. This intriguing visitor is most likely a natural interstellar object. The evidence points toward it being either a fragment from a larger celestial body that was torn apart by gravitational forces, or a chunk of solid nitrogen ice, similar to what might be found on a distant Pluto-like planet. Before Oumuamua, our knowledge of interstellar objects was purely theoretical, based on what we knew about the formation and behavior of comets and asteroids within our own solar system. Oumuamua's brief visit offered a tangible glimpse into the uncharted expanse beyond our solar neighborhood, confirming that objects can and do traverse the immense distances between stars. Moreover, Oumuamua has challenged our preconceived notions about what interstellar objects can be like. Its characteristics didn't fit neatly into our existing categories of comets or asteroids. This anomaly has prompted scientists to rethink some of the fundamental assumptions about how objects in space behave and interact, leading to new models and theories that can accommodate the unexpected. The implications of these findings are huge. If Oumuamua is indeed a fragment of a larger body, it tells us that the processes that form and destroy celestial bodies in other star systems may be similar to those in our own solar system. This offers invaluable insights into the life cycle of planets and the dynamic and sometimes violent nature of their environments. On the other hand, if Oumuamua is a piece of solid nitrogen ice, it suggests that the building blocks of planets in other solar systems can be quite similar to those in our own backyard, hinting at a universal recipe for planet formation. Oumuamua's visit has also shown the importance of continued observation and exploration. Each new discovery brings with it more questions, driving the relentless pursuit of knowledge that propels the field of astronomy forward. With advanced telescopes and probes exploring beyond our solar system, we'll discover more Oumuamua-like interstellar objects, each revealing more about our mysterious universe. The future of interstellar object research is more promising than ever. The key to unlocking more secrets of the world lies in our ability to detect and study similar objects that venture into our solar system. Oumuamua isn't the only time something like this has happened. Tuai Borisov was discovered by amateur astronomer Gennady Borisov, and unlike Oumuamua, was immediately identified as a comet due to its pronounced coma and tail, characteristics that Oumuamua conspicuously lacked. Tuai. Borisov's discovery was significant because it provided a contrasting example of an interstellar object, reinforcing the idea that such visitors can vary widely in their properties and behaviors. The comet's path through our solar system offered scientists a valuable opportunity to study its composition, which was found to be surprisingly similar to that of comets originating within our solar system. This similarity has led some astronomers to speculate that the building blocks of solar systems might be more uniform across the galaxy than previously thought. Another such instance is the strange behavior of KIC 84628852, also known as Tabby's star or Boyajian's star, named after astronomer Tabitha S. Boyajian. This star exhibited unusual and dramatic dips in brightness, which were first noticed by citizen scientists participating in the Planet Hunters project, which uses data from the Kepler Space Telescope. The fluctuations in brightness were irregular, unlike anything seen with other stars, and did not fit the typical pattern of planets passing in front of the star. Some of the dips reduced the star's brightness by up to 22%, suggesting that a massive, irregularly shaped object or group of objects was orbiting the star. One of the more sensational theories proposed that these could be megastructures built by an advanced civilization, perhaps a gigantic swarm of solar panels for energy collection. However, further research has favored natural explanations, such as a cloud of dust and debris from a disrupted planet or comet, though the mystery has not been entirely solved. The repeating fast radio bursts are another mystery that has fueled speculation about their origins, including the possibility of alien technology. Fast radio bursts are intense bursts of radio waves lasting only a few milliseconds, but releasing as much energy as the sun does in several days. Most fast radio bursts are one-off events, but some repeat in seemingly random or, in rare cases, regular patterns. One notable example is FRB 121102, discovered in 2012, which originates from a dwarf galaxy over 3 billion light-years away. Its persistent nature and the vast energy involved led to a flurry of hypotheses, including those suggesting an artificial origin. The repeaters lead to wilder speculations, including the idea that they could be signals from advanced extraterrestrial civilizations. However, natural explanations, such as highly magnetized neutron stars or black holes, are the leading theories among astronomers. Lastly, the discovery of Proxima b, an exoplanet in the habitable zone of our nearest stellar neighbor, Proxima Centauri, sparked interest for its potential to support life and for the mysterious signal detected from the direction of the star. Observations made using the Parkes telescope in Australia picked up a narrowband signal, BLC1, that initially appeared to fit the profile of a technological signature. The signal, however, was later attributed to human-made interference, a common challenge in the search for extraterrestrial intelligence. But what could these future discoveries reveal about the universe and our place within it? For starters, each interstellar object carries with it the story of its origin. By studying their compositions, we can glean insights into the chemical processes at play in other star systems, shedding light on how planets, and possibly even the building blocks of life, are formed. This could help us understand whether the conditions in our solar system are unique or common across the galaxy. Moreover, the paths these objects take as they travel through the galaxy could reveal new information about the structure and dynamics of the Milky Way. Are these objects flung out from young, turbulent star systems, or are they the remnants of ancient space catastrophes? With advanced observatories coming online and the global scientific community more engaged than ever, we are well equipped to continue our exploration of interstellar objects. Each discovery satisfies our curiosity and challenges our assumptions, pushing the boundaries of what we thought was possible. Oumuamua is just the beginning. Spacey is huge, filled with mysteries and wonders beyond our wildest dreams, just waiting to be discovered. And that's what makes the adventure of astronomy so incredibly exciting. Thanks for exploring with us on Beyond Discovery. If you enjoyed these revelations, click now on the next video that pops up on your screen. It's unbelievable.